Well, first of all, thank the organizers for inviting me. It's really a big pleasure and a big honor to participate in this conference. I will review some of the work of Marco Brouwer, Karl and myself, and actually the whole case collaboration on our work on testing gravity models with declensing. I also will show some results of our Phoenix cluster survey in dwarf galaxies, which is work done with René Pelletier and our PhD Sarah Efterkijn. So let me start, but since we are at the MOND40, I take the liberty to step back even 10 years more to the 70s, where a lot of things happened in radio astronomy. And I start with this epic picture, which is Professor Oort giving his lecture at the old observatory in Leiden, Sterrenwacht, Leiden, 1973. This is the last lecture in the old building. For those who don't know Professor Oort, he was actually the founder of the Westport Radio Telescope, so he's actually the founder of this club. And where all the H1 observations were done on flat rotation curves. And he was actually also the founder of the European SAMI Observatory. So what is noticeable in this picture is that the whole room was filled with radio astronomers. And actually I'm on the right side as a very young student and proud to be there as part of this enormous crowd of radio astronomers. Actually Leiden was the mecca of radio astronomy. All the radio astronomers came all over the world to visit Leiden and to work with it. In Leiden actually we concentrated mostly on continuum observations. And while in Groningen, a lot of work has been done on the H1, and clearly has led to Bob Summers being involved in this, and Groningen and Albert Bosma was actually the first to map flat rotation curves in the spiral galaxies. So I did my thesis in 1978 doing 610 megahertz observations of the Euclid cluster and also the copper cluster. And actually in those days it was really raining discoveries, one after the other. And it was a really fantastic time. This is the cover of my thesis, and you see the output of galaxy counts from Zwicky, the Zwicky catalog. And actually people like Tift and Terenghi were very keen on measuring the redshift from our active galactic nuclei, which we're detecting in the radio. So we were the first to get all these redshifts for the galaxies in this cluster, and we then discovered that the redshifts were more or less identical. In other words, this stuff here is really forming a supercluster. So in passing, we discovered superclusters and large-scale structure in the universe. At the same time, George Miley detected this radio source, 129. There's a very long radio tail. And the only way we could understand this very long radio tail is by assuming the thermal confinement of the radio block by a hot intergalactic medium. And we proposed, George Miley proposed, this hot intergalactic medium to have a density of the order of 10 to the minus 3, pretty high. And I can tell you later on this has been confirmed by X-ray observations. Actually, I proposed that these were the X-ray error bars of the Google and Area 5 satellite, and I proposed that this giant, supergiant galaxy there is most likely the source of a halo of X-ray, and we found about 40 of them more in our surveys. And we proposed them to the Einstein satellite to put them on the observing program. And actually the Einstein satellite did detect all of them. And this is actually the main core of the large number of detections of the identicals and CB galaxies, which have been published by Christine Jones and Bill Fournier. So it was really a very exciting time. Most important thing for this talk here is I will talk my way that this narrative of the 610 megahertz observations and the narrative of the H1 observations will join somewhere in the middle of my talk. But one of the long-lasting discoveries is this head-tail radio sources here at the outskirts of the supercluster. Again, applying the thermal confinement to the radio blocks here, we found that there must be a medium, intergalactic medium of density of the order of 10 to the minus 5. So an order of magnitude 1 or 2 or magnitude lower. Until today, this gas has not been detected directly yet with experimentation. So these are the first hints of a supercluster medium with a relatively about 10 to the minus 5 density. Same time, we derived the mostly function for X-ray sources. We detect, Einstein did detect all the ellipticals and direct ellipticals, didn't detect any spiral, and we detected the first mostly function of spiral, of elliptical galaxies. Right, so this is my little intro. Then we go to the VAR, but of course I don't have to explain what a VAR is. Since it's a very useful way to represent the data, it's a great idea. And I will use the VAR also in my presentation. You all know now that on the horizontal axis we plot the baryonic matter based on the stars and observation of the stellar mass, assuming a mass-to-light ratio, adding the gas. While on the vertical axis we plotted the nanometer mass. Well, the VAR has a few very good things. One is that you can get closer to physics by going to accelerations, so that's very good. Secondly, it allows you to combine data from different sources, from different observations. So I will combine it using virialized systems and rotational systems during my talk. So that's a very nice property of the VAR. One drawback is it's a little bit less clear how selection effects work and how errors behave, because sometimes it's not completely intuitive how that works in this presentation. Right, well, you have seen this picture already many times during the spot events. They are as defined by Stacy, as observed by Stacy McCoy and his colleagues. The fit there is an empirical fit, as stated by the authors, with a characteristic value of 1.2 10 to the minus 10. And we use that fit in comparison of our VT models with MOND. For EG, the story is a little bit different, a little bit more complex. The bottom line is that Verlinde predicted a characteristic velocity, characteristic acceleration of CH0 and we use that value for our models. Let me make a little sidetrack. We heard a lot of complex analytical and theoretical considerations. Let me explain that I do for this. Forgive me for doing this way also to Euclid. Eric explained now EG in a very simple word. In his 2010 paper, Eric proposed a certain area law to explain gravity. And he equated the surface area in terms of the surface area of a sphere in terms of squared Planck length. In his 2015 paper, he equated the effect of dark energy and dark matter in terms of the volume law, with the volume of the universe, or actually the volume of the dark energy, in terms of cubic Planck length. So the two laws, cubic Planck length and square Planck length. And actually the stress between these two laws is causing the value of CH0/6. You can make it very simple. You can say, well, it's for the same reason that an elephant has a very sensitive skin, dark matter emerges in this theory. So, I should make one note, right? I use the term prediction, and Eric claims very clearly that he also looked at MOND and phrasing his theory. So it is a prediction with a big star because he knew what to predict. So you have to be careful, and actually this whole business of comparing observations and analyzing observations, you always have to be extremely careful to be not have an opinion before you see the data. I can tell you that in the kids survey, where we do a lot of cosmological tests, most of the tests we do blind. Right? So all the calculations are first done, and then at the end we unfold the result, which is done by a third person. And on the CDM, although I don't have to explain you all this is circumstantial, there's nothing fundamental on the CDM which predicts this kind of relation. Alright, so this is my humble introduction to lensing. First, strong lensing, just as an appetizer. Well, you have seen probably this beautiful picture of the Hubble telescope, where a remote galaxy, the light of a remote galaxy passes along a bright galaxy in the center. They are aligned, we call them bright center, the galaxy in front of the lens, and you see this beautiful arc, I think you see them, of the strong lensing of a remote galaxy along the line of sight to the bright galaxy. Now, weak lensing is a completely different business and is much more complicated. The light of remote galaxies passes along the halos of the galaxy, of the lens galaxies. And the image of the remote galaxy, the distant galaxy, is deformed by tangential shear by an order of 1%. That's a very small value. We have no clue even what is the original shape of these galaxies. So the only way to get a feel of what this effect is, what is the effect of gravity on this weak lensing, is by doing very large statistics, big number statistics, as much as you can possibly get. Actually, this is what made us experts in big data. Are you ready?
Yeah.
All right. So what we do is we stack the signal of the lensing in concentric circles. So again, in concentric circles around a target, and stack the signal and divide a radial path of the so-called excess surface density, so the gradient of mass in that circle, a function of radius along the centered on the target. So in weak lensing, we measure the excess surface density of mass. It's big work. It's incredible amount of work actually to do this, and it involves doing very large surveys, deep surveys. It involves to measure redshifts for all these galaxies. So we try to get as much spectroscopic redshifts as we can, but we add photometric redshifts. It requires very high quality observations. It is very good seeing, very good point-spread function, as we call it, to use. In case we use only data with a seeing better than 0.67 arcseconds in parallel, and G. And for Euclid, the satellite will come up in a moment, we expect a point-spread function of 0.2 arcseconds to do this work. Well, there's a lot about this point-spread function. This is really very complex. It's not as simple as it was 20 years ago. A lot of effects. If you want to do this very high accuracy measurement, you have to take care of the atmosphere, you have to take care of the focal plane geometry, you have to take care of the color term. That is true for Euclid. The galaxies have a color, and they all have a different color, and there's a color term in the instrument, and so in effect, every galaxy will have its own point-spread function because of its color. That's what we call effects in the filters. There's digital of the telescope, and there's also detector electrons. And I only mention now those points which are related to point-spread function. And many more. And this was actually the reason that we built the Observation Information System, a complete new system, because we knew this started in 2000 actually in Edinburgh. And we built this system because we knew we were going to handle enormous amount of data. It was in the time that we had the 1 megapixel on your telephone already a bit, a lot. And we had to, we built a new system where we maintained all causality between all the different data items. And I'm not going to elaborate on that, but this system has been used for the analysis of the weak lensing, and actually the same system is now going to be recycled, and has been recycled for the Euclid satellite, and we're going to use it there as well. Just to give you a little bit of flavor of, you know, what is behind all these few graphs I will show you in a minute. while we were building all this very complex information systems, at the same time we were dealing with theories of gravity, which is based on the holographic principle, I got the notion of there's an information universe out there and there's an information universe down here in our computers. And I started organizing a series of conferences in my planetarium in Groningen. And on this I'm proud to show you perhaps the lineup we had in the last summer. We get people from different disciplines discussing these matters. All this is on the Information University YouTube channel, which is actually very popular. Now back to the work on the lensing. We used the Omega camera, which we built ourselves. We started in 2000 with this, and the signal was heavily delayed. We could only start observing in 2012, and all the observations were done 2 years ago, and its final data release has just been published a few months ago. Kits, we use 1,000 square degrees of the 1,500 square degrees of kits for our paper. The paper is Margot Brouwer. I mentioned them again because we did an enormous amount of work and And the first thing we did is for testing modified gravity, EG, and on the CM, we selected isolated galaxies. And our isolation criterion was no other galaxy within 3 megaparsec with a mass greater than 10% of the light. That was a very strict criterion. Second criterion was that the stellar mass of the lens should be less than 10 to 11, so to avoid bright central cluster galaxies. We measured the excess surface density in a radial range of 30 kiloparsec to 3 megaparsec. And I should re-emphasize again and again, this is our enormous distances. We are very far away from the galaxies, and in many evaluations, we can use a point source model for understanding the observations. I'll pass the M over L ratio stories, but I go through this since I see I want to use a lot of time. In the end, we ended up with a sample of 259,000 galaxies for which we measured them. This is the picture of the press release, and you'll see the well-known results from spirals, and this is the result from the Z-lenses. I plotted this on top of M87 to remind everybody who looks at this, this is a very deep image of M87, how far away we are from the galaxies in these measurements. Well, you can see the has been extended by 2 orders of magnitude. It's blindly maps directly to the defined by the spirals. It follows the square root G bar relation. And we have 2 completely complementary techniques, right? H1 radio, Z cleansing, which actually show the same relation. There's a first notion here is that the error is extremely small. And by now, one can say that we know the distribution of the dark matter better than that of the baryonic matter. So our biggest problem in the expectation is understanding the baryonic matter. The error bar here on the top left, the error bar here, the shaded error here, that represents systematic errors, which is an uncertainty in the adopted master light ratio. So the adopted master light ratio probably is even a larger error than this sampling error of our lens. All right, then one of the what you might notice here is that it's a little bit above, right? And it's within the it's not within the air. So one of the first things we did is to split the sample in 2 parts. And we used the Circumgalactic index on the left picture, surface index 2, and the color index to discriminate between the early types and the late types. And you can see when you do that for this sample, there's a major difference between the 2 samples. There's a major difference in the R of spiral galaxies and the elliptical galaxies. It's at least a factor 1.5. The 5.7 sigma, which is actually quoted in our paper, refers to this one here. On the right one, we could not even get a sigma because it's out of space. In that respect, it's a very significant result. It's notable that this result is also obtained in this regime, where we're pretty sure that our photometric redshifts and redshifts are okay. You see at the left part of the diagram as a warning sign, we use photometric redshifts, and at larger distances they can be more uncertain. So we said, well, this is a warning sign. We have to be a little bit more careful in this interpretation in this part of the regime. And you are pretty confident you're doing the right thing. And also there you can see the difference. Well, to explain the difference, you need a difference of an N over L, adopted N over L, master light ratio of the size of 0.4x, which is huge. And so we have a little bit of a problem to explain this observation, this MOND over EG. Then I come back to my introduction, since I have this history in X-ray observations. And when we did this, I remembered, what I did in my thesis, these are together things. And I remember that we're detecting electrical galaxies all over the place with those piles. And I just started to look up the literature and what is evolved. I mean, how has this subject evolved in all those years? Well, the bad news is that it has hardly been evolved. It's rather surprising. This is actually the very best sample, at least what I can find, of X-ray mass on hot circumgalactic matter, which we have used that term earlier. The hot circumgalactic mass around early type galaxies determined by the Fundamental observation. Well, you see there is a scale. There's a scaling relation. It's not so easy to find, to make a conclusive statement out of this. What we did is that, well, if you look at our galaxies here, which are in this mass range, on the elliptical galaxies, we expect that the X-ray circumgalactic matter will be in this range of their diagram, which translates to a stellar mass to X-ray mass of 0.1 to 1. That's within 5 times the effective radius. Since we go extremely far out, if you transpose that to a much larger radii, you have to multiply this number by a factor 3. So this best X-ray observations we have at this moment, we know that you could expect a X-ray circumgalactic gas of the order of 1 to 3. So what I did is as a postulate, let's postulate that this is the case. And then I get this result. If I suppose that the galaxies we observed in the kits have a certain gas of the order of the stellar mass, and 0 for the late type galaxies, then the whole difference is gone. So I think I've said already most of the things I wanted to say in this state. Clearly, again, the uncertainties in the amount of a circumgalactic matter, gas, is still going to be a trap for all our observations in Euclid and in the future. That's simply because the surface brightness of X-rays with a temperature lower than 10⁷K is so low that we cannot detect. Sometimes it's good to remind each other, we see all the beautiful things, but there are a lot of things we don't see. And one of them is the circumgalactic gas with temperatures lower than 10⁷K. The other thing I should mention, I meant to mention, do it again, do it now then, we are still completely blind to molecular hydrogen. Molecular hydrogen with temperatures below 100K we cannot detect, although we know that at least there is as much as a neutral hydrogen, and could equally be much higher in the circumgalactic. Anyway, this is a technical slide where we put our uncertainties together for those who want to discuss uncertainties. The interesting thing is that we also put the gamma data here. This gamma data is a survey where we have spectroscopic redshifts. So it's a smaller sample, it's 180 square degrees instead of 2000. And you see that the gamma data, this is the blue points, match to the black points, which is the set with a lot of photometric redshifts. So that gives us some confidence that we do things right. The other thing is you can just compute the dispersion of the individual measurements, because the individual measurements are independent of each other. And if you compute the standard deviation of individual measurements, we get for the kids 1000 survey, we get a number of 0.7 dex, and for the gamma 0.16. So that number, the individual dispersion of the data, matches actually very well to our L boxes. Our L box actually even a little bit large. And it also matches to the scaling of gamma, and the kids survey, the scale is also perfectly matching. So it gives us confidence that we're doing things right. We have also, of course, to account for systematic errors, and the most dominant one is the M of L, as I just mentioned. This is on here, so 0.2 dex. And there is also a smaller systematic error, which has been elaborated by Carl Mann, and he could easily give a whole keynote on his measurements on the cosmic simulations and measuring the R in cosmic simulations. He came to the conclusion that in the domain of what we observe here, the systematic error in the R, because of the mass model you always adopt, is implicit, is of the order of 0.05. So I think we're doing fine. Also the isolation criterion is confirmed by the gamma data, and this is where we stand. But then, ladies and gentlemen, there is breaking news, and that is this one. And this is actually the first time I present this on an international forum. This is actually data from e-Rosita, and we have been hoping and wishing that this data would come. And they have e-Rosita as an X-ray telescope, and they have spec'd the signal of 25,000 galaxies. And actually, these are the same galaxies which are in our survey. This is the gamma sample. They had a completely different scientific objective in mind. They were splitting the sample in fluorescent galaxies and star-forming galaxies. They didn't discuss any cosmology or gravity or whatever. But this is their result. And the result is that they find that the early type galaxies of this overall, with the stacked signal, are at least a factor 2 brighter than the late type galaxies, and you can see it propagates over them. So this is really, I hope, good news also for MOND and EG, because this notable difference in the R of early types and late types can be explained with circumgalactic matter, and there is now for the first time an indication of a measurement of X-rays of this very low surface brightness galaxy, or surface brightness X-rays, that this is really there. To be added, I didn't say that yet, but clearly this is also matching to the missing baryonic matter. So we solve a lot of things. This should solve a lot of items in the same way. Right, then there's one slide. Where am I in time? Okay. There's one slide on the enormous amount of work which Karel Mann did on measuring the R in simulations. And I will be quick about this one because there are more things I want to talk. He measured the R in the Bahamas simulation, which is this graph here. This is the error bar. And you see it's a little bit off. And of course, he says, well, I can get it right if I change the stellar mass to stellar halo ratio, can be made right. And of course, the shape is Mondium, so to speak. The mice observations, for which you also determined the R, are this one here, and the red shaded area represents the errors in the photometric in the redshift. And actually it does very well. But it's very nice, it's good, so LCDM is able to produce dwarf, that is a statement one can make. On the other hand, one should note that these simulations are tuned, and they are tuned to the observations all the way. They use the color distributions, they use the velocity functions, they actually tune their simulations to the observed universe. These are not simulations from radio. And that makes it very tricky, particularly because of the hydrodynamical simulations. There are two very strong nonlinear effects, which is feedback and ionization. It's very difficult to model, so the best way is to tune the parameters and get things right. And I talked to Euclid, which is the chief of the ego simulations, and he assured me, yes, that is what we do. Never draw any cosmological conclusions from this kind of work. We only say we do this and then we get this. That is, you cannot use these simulations as a test to understand. That is maybe the reason I don't spend more than 5 minutes on this now in this presentation. So that's my conclusion. I'm sure Karl would say something different, but this is how I look at it. Then I would like to spend 5 minutes on the dwarf audience, because it's clear now that on the big lensing we have not been able to make any discrimination between MOND and EG. So that's a little bit frustrating if you want to test both of them. Now, it's important to note there's one big difference between MOND and EG, and that is EG, the prediction is for the mass, excess mass density, the mass within a certain range. There's this term here. This is the mass gradient, which is not in MOND. So, this is a prior which could discriminate between MOND and EG. And I know, Levy, you have, some colleagues have been looking for this. This could emerge in dwarf galaxies. Low accelerations, this term can show up. That has been done here. I think it's very well. And the result of this term is that at low accelerations, the dwarfs will appear a little bit above the standard range. And you can see the airbars are very big, and there's a good reason that they're very big, because it's nearly impossible to do this. We contemplated to go to the ELT and do a MUSE dedicated program, and then we computed we need 3 months of observations, and then the program committee will say, no, you can't do this because the spectral resolution of the MUSE instrument is not good enough. So simply we are not in a good, well, maybe someone knows a better way, but our view is that it's unfortunately impossible to do. So then we are a little bit in trouble. People are focusing on single powers, and single objects, exotic objects, and then of course there's always the problem of inclination correction. There's the problem of whether they are dynamic or stable or not, which we know they're often not. And there's also the problem of cool molecular hydrogen. So that's also not the way to go. So then I worked with René Pelletier on the Fornax cluster survey, and we identified 36 dwarf rhodials, which are brighter than the dwarfs which Nelly has observed in the previous plot. We had 7 hours per field, and we did the integral field spectroscopy, and we could this is actually a very important plot. We measured the velocity dispersion, say in a handful point, at various radius for this 36 dwarfs. And what you can see is that the velocity dispersion is a flat line. In other words, these galaxies are realized, so we are now pretty sure that we have a sound sample of realized objects which could be useful for our experiment. Then here are the galaxies, and then go straight away to the R of this 26 dwarfs in Fornax. And as you can see, they follow the R pretty well. There are 3 outliers out of 36. I don't think it's statistically significant. So in fact, these dwarf galaxies do follow the R pretty well. That's good. That's nice. But what is the main message here? Well, there are 2 messages actually in this sample. Because on the same paper, we also told the fundamental plane and often it's right. So the dwarf galaxies have much higher, much more dark matter than darker galaxies. How can it be in the MOND and in EG? And actually, what you can see here is we show that they match the var, but we also show that these dwarf galaxies follow the alternate straight. So there are galaxies, these galaxies follow the fundamental plane. For theoretical considerations why you think this should be the case, but it is very nice that it is observed. So actually, this solves the riddle of high dark matter in dwarf galaxies in the context of MOND and EG. So, well, I plot all this stuff in one graph. It's a little bit ugly, but it's all there. The phonics, the spirals, and the reclensing. There are a few notions now. I think the result of the dwarf galaxies is more than just casual. It has something to say, because these dwarf galaxies have a typical scale of 0.6 to 1 kiloparsec. And the var is observed on the same scale as the same var has been observed in the parallels with 50 to 100 kiloparsec scale. So we get the same relation, and of course you probably like it, but we get the same relation, we observe the same relation with a factor of 100 different scale at the same acceleration. And that is clearly something which is, I find that a very strong point. And it would be extremely difficult to assemble this by circumstantial effects in LCDM. So that is actually my main conclusion when I plot the data of the phonics dwarf modules in this diagram. That's the scale invariant of the var. I prefer to call it scale invariant rather than a law. That the var is a scale invariant, and clearly the phonics dwarfs make the case. Now, you really want to discriminate between EG and MOND. Clearly, it could be done on the basis of the SASIC index, right? All the samples. We try to do that, but it is extremely difficult, because if you use the SASIC index not on the log-to-log scale, you see all these gradients all over the place. And if you sketching all these different galaxies with all the different gradients, I think you will be lost. Maybe there's a bad person here in the audience. I invite you to spend 2 years of your life to do this, but there is a possibility that we can get this out of the reclensing net. And then to get the DM, the R term, as a pair, and see whether it works or not. Will be your ultimate test. The other ultimate test is actually where we built Euclid for. To be honest, we started already building Euclid in 2009, even before we started observing this Omega. It's quite strange, but we are now really ready for Euclid. And the most important thing there is for Euclid, it is really designed to do all this assumption of redshift, out of the redshift of 0.2. And up to the redshift of 2. And so this is the main science case for Euclid. Cosmology, there's of course also the SAMI omega matter tension. It is clearly also a objective for Euclid, the large-scale cosmology. But Euclid is going to be able to discriminate these models, provided we have the models. So this is one of the things I would call upon. We really have to make models also for MOND, which you can predict what Euclid would see, rather than making it work after the fact. So that's so I talked to Erik a little bit and said, I presented this on the last Information Universe conference. This is the first very I don't dare to call it the back of the envelope model, but you had a lot of disclaimers. This is just the first attempt of it to do this. That this is a graph of the predicted ratio between the dark energy affecting dark matter energy compared to London CDM, which actually has a strong variance between 0 and 2. So, I'm not going to do details but that's really what we are after in the Euclid experiment. So the good news is 5 minutes after the Euclid experiment is, there's good news that Euclid is going to be launched. It's not formal product yet, but I can say it here in this room that the launch will be on the 1st of July. Okay, Canaveral is a SpaceX rocket. We're ready for it. It will measure 2 billion, it will measure 2 billion galaxies, near-infrared spectra of about 35 million. It will survey the extragalactic sky with an unprecedented amount of data. On the left side here, there's the Hubble Deep Field, which is about 250 days. On the right side, this is what Euclid will do in 4,400 seconds. Really not as deep as Hubble, but we still get 300,000 galaxies in every observation of somewhat more than that. So we will map the whole sky, extragalactic sky, which is about 1,500 square degrees. You avoid the galactic plane, you avoid the elliptic plane, and there's still 1,500 square degrees of space left over. And we will map that, and we do exactly the same job, well, the same kind of things which we have been doing with STIX in America. But then as a function of redshift. So there's a lot of work in getting the redshift right in Euclid. So it'll take about 5.5 years to acquire this data, but the first data releases are expected in November. And the first scientific evaluations are expected in a year from now. All right, so I will take I made a little Excel sheet, MOND on an Excel sheet, of my conclusions. And I thought, well, since I started with the Ort School, and clearly Ort was also one of the people who was on the Simon School. I remember then this BBC interview with Feynman. He gave many BBC interviews. But one of these interviews, he was asked the question, what are the criteria to accept a hypothesis? And he answered, of course, good physics and good mathematics, predictions, and the last one made a lot of impact to me is that you must also have an avalanche of small things which become understandable. And this is clearly where the observations come. So this is the Excel sheet, this is my last sheet, Mr. Chair. I will go through it very quickly. First of all, my opinion is the jury is still out. So before everyone dies on me, the jury is still out. I think we are not conclusive yet. We have learned what we want to do with Euclid. I don't have to elaborate on the physics of MOND. In EG, I already told you the basic principles. We should realize that in EG, acceleration has a temperature, and also that this is an extremely heroic theory, because in the end it means to explain dark matter and dark energy and quantum mechanics, TR unification in one go. So one could also look at EG as a class of models, and there could be more instances. Well, and then at the end, there is nothing fundamental, it's only circumstantial. In terms of three parameters, well, in the empirical value of MOND is probably 1. If the AST effect is leading to a lot of parameters which probably you also don't like, then it will be 2. In EG, there is a 0 free parameter, but there is a big star on it, as I already said, because he knew what to predict. In London CDM, there are lots of free parameters to do the job, and at least 2 on the non-linear effects, but there must be many more. The scale invariance of the dwarfs I just mentioned, which is positive for MOND and EG. The scale invariance of the bar presented by Stacy is also the very small error bar. I remember where you are. There you are. Yeah, the first time we looked at it in Italy, the first surprise was a very small error. And we could put this in the avalanche, but I think that is really a very important, becomes a much more important point as far as I'm concerned. Z evolution, that's, you heard what I just said. Of course, LCDM is doing very well there. And then in my personal evidence is that the effect that we solve the riddle of the dark matter in dwarfs and that they are on the fundamental plane is fine. The missing baryonic matter. My last takeaway messages is we do know dark matter now better than baryonic matter. We have to find a workable prior for discriminating EG and MOND. We need to predict the Z evolution between Z0 and 2 in order to make progress with respect to the observation. And, but still, hot circumgalactic matter will be a big challenge for you. Thank you.
Thank you.